So now what I'll show you is how to do a scatter plot using a TI-83. Now I have an emulator. You may own a TI-83 or TI-84. So I'll show you how to enter that data. So duration are all my X values and time is all my Y values. So in my emulator, I'm going to go stat, and then I'm going to push number 1. And in L1, you see I put all my data. You have to enter it very carefully to make sure it's exactly as the data exists in your table. Once you're done, cursor over to the right and put the corresponding Y values in L2. Once you have that information, what we're going to do is we're going to do a little housekeeping. What we want to do is we're going to go down here to second catalog, we want to push the D button. Notice there's A, B, C, D. Push the D button, jumps to the D's. We want to scroll down to where it says Diagnostics On. So notice my little black cursor is pointing at Diagnostics On. So I'm going to press enter, or then you press enter again, and Diagnostics is on. Now that I have all that information, all the X's in L1 and the Y's in L2, I want to do a scatter plot. So what I'm going to do is I'm going to go second Y equals, which is my plot. I'm going to choose number 1. I'm going to make sure that plot 1 is on and that I'm using L1 and L2. And you can use whatever symbol, the mark you want. And you can use, if you're a color calculator, you can choose whatever color you want. All right, so mine's on, so that's good. So then I'm going to do second format. Nope, just format. Just do this button right here, zoom. And I'm going to do number 9. And notice that it plots all my data in a scatter plot. Now this scatter plot shows positive correlation. You could draw a line of best fit through this data. Now notice we don't use Minitab. You could do the same thing with Excel, but our plot looked exactly like the TI-84 plus one. So the scatter plot appears that the variables have a positive linear correlation. Coefficient of correlation coefficient. This is a measure of the strength and the direction of a linear relationship between two variables. The symbol R represents the sample correlation coefficient, R. This is the crazy formula, but we're going to use technology. I mean, you can use, I'm going to show you how to use Excel spreadsheet to figure this out, but if you enter all the information into Excel spreadsheet, there's a much faster way of coming up with R than using this crazy formula. The population correlation coefficient is represented by rho, which kind of looks like a script P, but it's pronounced rho. The range of the correlation coefficient is from -1 to 1. The stronger it is to -1 or all the way to 1, the greater the strength of the correlation of the data is. Very strong. A perfectly straight line going uphill will have a +1, and a perfect straight line going downhill will have a -1. The closer you are to 0, the more scattered all the data will be. Perfect -1, 0, +1. So this data, which is going downhill, is a -0.91. That's pretty strong. Later on, we're going to test to see how strong things are. But right now, if you, say, rule of thumb, are you a -0.8, -0.8 or better, it's pretty strong. This is a 0.88, which is a strong positive correlation. This is a 0.42. Notice it's below 0.5, so it's weak. It's kind of going uphill, kind of. I would say I could make an argument that the data is kind of going uphill, but I'd have a hard time making an argument that it's negative correlation, because it's really not going downhill, primarily because of these points right here. And this is a 0.07, which is, there's no linear correlation at all. Which way the line is going, I would have no idea. So, going over that crazy formula, sigma x is the sum of all the x values. This is the sum of all y values. This is the sum of the product of x times y. This is the sum of the x value squared. This is the sum of the y value squared. And using all those amounts, and n is the number of ordered pairs, you would calculate the correlation coefficient using this formula. So if we did this with an Excel spreadsheet, this is what we do. There's all your x's, there's all your y's. You take the two columns, you multiply them together and add them up. Then you take the first column and square it, add them all up. Take the second column, square them, add them all up. Then you'd plug it into this nasty formula, and you'd end up with an R of 0.882. And 0.882 suggests that there's a strong positive linear correlation. So, how do we use technology for this? All right, so these are the same data points we put in our emulator before. So we're going to go back to our emulator. So I would do stat. Now remember, we had turned on diagnostics. Now we know that it's a positive linear correlation because we saw the scatter plot. Now we're going to calculate. We're going to go over to calc. Number 4 is linear regression, so we're going to push number 4. Then we're going to enter L1, enter L2. Keep going until it says calculate, and boom. Now, here's our formula. This is our formula of the information y equals ax plus b. You may remember this from Algebra 1. This is our slope, 12.488. This is our y-intercept, 33.68. But what is of interest is our r. Our r is a positive number. It is 0.9786592129. It's positive, and it's very close to 1, which means it's strong positive correlation. So these are the same information. Make sure you have diagnostics on. You go to calc, you go linear regression. You keep on pressing enter until it calculates your correlation coefficient. Ooh, I want to go back for a second. Notice in Excel, if you're using an Excel spreadsheet, in the cell where you want that information, you would do equals capital CORREL, close parentheses. You would highlight your data, This would be your x values, this would be your y values, and then it would calculate your correlation coefficient for you. So this would be the formula, and this would be the output. So you can use Excel, or you could use a TI 83 or 84. So using a table to test the population correlation coefficient P. All right. So in your book, table 11, in Appendix B, you will have information about the absolute value of R is greater than some critical value listed in your table. So that table is important. So you all have books. So if you're doing the classwork or homework, I will get hold of this table 11 appendix in Appendix B and get a copy of it for you. Otherwise, use the book. All right. So in this book, let's say if we want to see if rho is significant for 5 pairs of data, so n being 5, at a level of significance of alpha, which is 0.01. So if it's equal to 0, so if it's greater than 0, then it's significant. So we go to 5, right here. You go over to 0.01, and it's 0.959. So because the absolute value of R is greater than 0.959, the correlation is significant. Okay, so this is the using a table to test the population correlation coefficient against rho. R being 0.97, which is greater than 0.95, so it's significant. All right, so here are the steps. Determine n. Determine whether you're going to use 0.05 or 0.01. Look up the information in Table 11 in Appendix B. Compare the absolute value of R to determine whether it's greater. If it's greater, then it's significant. Otherwise, it's not. And then just explain it based on that information. All right, so here we have our R is 0.0979 for 25 pairs, so n is 25, and we want to do a significance of 0.05. We go to our table of n of 25, 0.05, 0.396, and we notice that 0.979 is greater than 0.396, so it is significant. So now we're going to use hypothesis testing for a population correlation coefficient of rho. So we can either have one-tailed or two-tailed. The question, when they ask you to do a hypothesis, they have to tell you whether it's one-tailed or two-tailed, because that's the table gives you different values to test against based on whether it's one-tailed or two-tailed. So if it's a left-tailed and rho is greater than or equal to 0, there's no significant negative correlation. If it's less than 0, it is significant. If it's right-tailed and it's less than or equal to 0, there's no positive correlation, but if it's greater than 0, there is significant positive correlation. If it's two-tailed, if rho is equal to 0, there's no significant correlation. But if rho is not equal to 0, there is significant correlation. So in each one of these hypothesis testing, they have to tell you whether it's left-tailed, right-tailed, or two-tailed. All right. So we're going to figure out a t-value called the t-test of the correlation. So the test statistic is R. We find out R, then using R and sigma, which they show you the formula for sigma, it's the square root of 1 minus R squared over n minus 2, where n minus 2 is the degrees of freedom. All right, the degrees of freedom is always going to be n minus 2. You can calculate t, and you need t for the table. In this text, only two-tailed hypothesis tests for rho are considered. All right, so we're going to do two-tailed. All right, so we have the state the null and the alternative hypothesis. We're going to identify our significance level, either 0.05 or 0.01. We're going to identify our degrees of freedom, n minus 2. Then we're going to go to Table 5 in Appendix B to find out the critical values and determine whether it's significant or not. And of course, we calculate t, the standardized test statistic, using this formula. Then, based on whether it meets the hypothesis or not, we determine whether it's significant. All right, so here's an example. With this GDP versus CO2, we got an R of 0.882. And we want to test the significance of this correlation coefficient using a 0.05 as our critical. Because it's two-tailed, our hypothesis 0 is rho equal to 0. We're going to see if we're going to reject this or not. Otherwise, if it's not equal to 0, then it's significant. Our level of confidence is 0.05. Our degrees of freedom is 10 minus 2, which is 8. We calculate t using this information. R is 0.882 over the square root of 1 minus R squared over our degrees of freedom. So t is 5.294. We go to table 5 in Appendix B, and our value t sub 0 is 2.306 in the table. I don't have I can't show you the table here, but in the back of the book, if you go to Table 5 in Appendix B, you go to n of 10, and you go over to two-tailed with a significant confidence of 0.05 and look down, you're going to end up with 2.03. And our decision, since 5.294 is not equal to 0, that our t sub 0 is not equal to 0, then it's significant. At the 5% level of significance, there is enough evidence to conclude that there is a significant linear correlation between gross domestic products and carbon dioxide emissions. Now, why is it important to figure out whether something is significant or not? Well, that's what we're going to go into next. Correlation and causation. The fact that two variables are strongly correlated does not mean, in itself, imply a cause and effect relationship between the variables. Just because two types of animals grow well in a certain area doesn't mean that the cause of one growth of one animal causes the increase of the other one. You may plot the data of one animal against another animal, and there may be very strong correlation, but there's no cause and effect. So you have to look out for this type of situation. If there is a significant correlation between two variables, you should consider the following possibilities. Things you got to ask yourself, a little common sense. Is there a direct cause and effect relationship between the variables? Does X cause Y? Does the reverse, does Y cause X? Because that'll change whether one's a dependent or independent. Is there a third possibility that may cause X and Y to be related in a positive correlation? Or could it just be happenstance, coincidence, that the two are related? I mean, in Iceland, they did this study once, relationship that the storks, number of storks over the years kept going up and up and up. The population kept growing. But did you know that the population of humans in Iceland over that same time period kept going up and up and up? So if you plotted the growth of storks versus the growth of human babies, one can conclude that there was a strong correlation. You know, the more storks you have, the more babies there are. But you know, and I know, that storks don't deliver babies. It's just a coincidence that the two of them had a strong positive correlation. All right, so here's a summary. You're introduced to the linear correlation, independent and dependent variables, and the types of correlation. Negative, positive, none. Found a correlation coefficient, R, which you could use in Excel or a TI calculator. Tested the population coefficient rho using a table, table 11. Performed a hypothesis test for population correlation of coefficient rho, table 5. And we talked about causation, cause and effect of correlation, and why you have to ask yourself, is there a cause and effect relationship?